Hey guys, gym term should be 2B. I forgot to make it a B. Second midterm. Gonna try to get through this pretty quickly. I apologize. I just have literally zero time in the past couple of days. But I mean, at least for those of you that need it, it'll be up before the midterm. Cool. All right, so let's just, let's not waste any time. Let's just get into it. So the questions in this one were a bit more conceptual, but a big theme was to kind of combine chapter 21, 22. This one really doesn't do that, but just an idea. We have a diphenol. If you see a diphenol, that's a buzz for, especially when you see the Jones, right? That's a big buzz for the quinone. So you form the quinone here. And then really the nucleophile can attack anywhere here. It doesn't matter, but the point is when it does, right, it rearomatizes the ring. It can be anything, so we can just make it a CN, right? But can really be anything, right? I think the craziest nuke you guys could probably get is like an enolate or something. But I mean, that wouldn't really change much. That would just add in like that, right? So cool thing. Just set there. Cool. Not much you can do with benzylquinones, right? I mean, there are things you can do with it outside of these, but what more can you do other than oxidize a diphenol and then react with the nucleophile? So it's not too crazy. If you see it, it'll probably be the same. Cool. All right. We have an amine, we have Hoffman condition. So a lot of you probably did what I always talk about, which is, turn this into NR3 plus. Consider this is the alpha, so then these two carbons are beta, right? So you consider beta, beta, they're both CH2s. So maybe you look at alpha, and alpha is also just the same. So it's very easy to just instantly go ahead and say that both alkenes are a possible product. Right. But again, keep in mind, we're trying to think about how to tie multiple concepts together. When I look at this beta here versus this one here, I'm thinking of a special B word or a word that, even starts with a letter of what multiple or what predictive product this is that might help me explain why we see more selectivity towards this product as opposed to this one. Right. Look for B word, I'm looking for benzyl, right? Benzyl positions are activated. Right. And so when we think about the elimination, yes, they're both CH2s. So there's equal amount of, ability to attack on either side. But this is benzyl. So these H's are way easier to take. So in fact, the major product will always be the benzyl alkene or the conjugated alkene. So always look out for that, right? Yes, we do go for the quote unquote unsub, quote unquote unstable alkene. But in both cases, right, both alkenes are equally substituted. And they both originate from equal subcarbons. That's really the big thing, right? They originate from equal subcarbons. So of course, we can go and think about other things that might promote one over the other. Because I know this is going to be asked, what if this were a trisub? Then yes, this CH2 would win. And now you have the other product, right? So in this case, benzyl would lose out, womp womp, but that's okay, right? Because that wasn't the point of the question. The point of it was to show a possibility of two alkenes where one is a more stable benzyl. Okay, cool. All right, moving on. This one got a couple people, and I'll talk a little bit about this why. But again, when I think about this chlorine and this chlorine, a certain B word is floating in my head. I think benzyl. And so this would be sort of a benzyl solvolysis question or SN1 type question where it's easier for the alcohol to attack at this position than it is at the other. And so a lot of people, when they saw this question, were really confused because in class, you guys talked about how EDGs are technically, they're used in these type of reactions. That is true, right? EDGs increase the negativity of the ring, which promotes SN1 because you can have a higher positive charge buildup or stability of that positive charge, right? These are very good charges together. So yes, EDGs do increase the reaction rate of this, right? But that doesn't mean that they're necessarily required. It's not the only thing that's possible. You can totally do these reactions without it. It just takes a little bit longer. So a very good concept here then is that EWGs would slow down the reaction. So you could be given a couple of these where there's like an NO2 at the end or like an OCH3 and just ask, when these guys are in orthopara positions, which one has the highest, reaction rate or the lowest reaction rate. Keep in mind though, right, we have to be orthopara to the benzyl position. So while this guy here, right, is a very good activator for benzyl SN1, right, having the OCH3 in a meta position is not going to be so good, right, because you don't have that resonance stability, right? You don't have that resonance stability there. A little bit impossible. Now, one thing that I'll key you guys into, a way to think about this as well, is that like an OCH3, for example, can boot off a chlorine, right? And it makes sort of a quinone type molecule, right? This is sort of a quinone type molecule. So why am I keying you guys into this, right? What's the point here? Well, I want you guys to consider that whenever you see these oxygen or nitrogen orthopara to some, benzyl chloride or benzyl bromide or whatever, those are essentially hyperelectrophiles, right? They're quinone type electrophiles. That might help you guys out on a particular explanation question on a different exam. Okay, cool. But yeah, this guy would suck because it's meta. And then again, I mean, if I had the NO2 instead of a chlorine, this is very, very bad because now you have a withdrawing group that's, orthopara to a chlorine. That puts the positive right on top of that, positive that you want to form. This will almost be an incredibly so, if not non-existent reaction. But if I had that NO2 meta, right, it wouldn't be so bad, but it would still be pretty bad. So this would be double smile down, but this would be just one smile down. Okay, or one frown, double frown, and then one frown. Okay, cool. All right. SN2s are also very good. So I guess maybe if I made this an SN2, you guys would have been more convinced as to this working. That would have worked perfectly well. Cool. All right. D is one of my favorites on this because, a lot of people get the first step, but then the second step kind of evades them. Organometallics add into the carbonyl there, and then we just heat this up. Now, again, think about reactions that only require heat, right? A couple of them might come to mind, like a Diels-Alder, which is a cycloaddition, right? But other than that, right, this is sort of like a electrocyclic reaction. Electrocyclic reactions kind of just rely on heat. So you might even remember like opening up cycles with just heat, right? Electrocyclic. So can you think of any other electrocyclic or maybe a sigmatropic reaction that can happen here? I definitely can. I can think of the cope and the Claisen. So the cope and the Claisen, right, they require some kind of 1,5 diene system. So in terms of if you were to name this, you would say 1,5 diene in the name. Best way to check for that is you count from one alkene to the other. 1, 2, 3, 4, 5, and 6. You get 6 total atoms, right? Where 1 and 5 are where your alkene are. Okay. So this is a 1,5 diene. For the cope is super simple. You kind of just draw a cope like this, right? And then just looks like you're literally looking in a mirror, right? It's like you're looking right straight in a mirror. That's all you got to do. And then you kind of count from one side. So I like to count from the top right and then go counter, right? And here's you got to be careful. A lot of people take this and think that this is now 1 because this is open and this is open. But the numbering must always stay consistent. So if top right is 1, top right here must also be 1. Okay. And so 1, 2, 3, 4, 5, 6 to 1, 2, 3, 4, 5, 6, right? This here is a representation of the original molecule. So I can almost even get rid of it because that's the original molecule. What I care about is the cope, right? The coped or the rearranged molecule. So now everything is kind of lined up, right? 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. I just got to report where these things go. So on 1, I have nothing. 2, I have nothing. 3 has a methyl. So I add it in. 4 has a methyl and an O-. So I'll kind of squeeze those in together. Okay. And then 5, 6 have nothing. Now, looking at this, this may look a little normal, but again, we have an O- which is adjacent to a pi bond. This is an enol. And this enol will tautomerize and form this ketone here. Okay. So you guys might remember that copes in general are, so generally copes are in equilibrium because, there's really nothing different from this guy to this guy. So the best copes are the one that have some driving force or some, some effect occur that allows them to be, more stable on the product side and push the reaction forward. So I have a very high KEQ. One of those things is when you turn, you turn one of the alkenes into a stronger bond, or in this case, right, we had a C double bond C here, right? But we tautomerize it to C double bond O, much stronger bond. So that pushes the KEQ to this very far to the right. Other things that can push it far to the right are if I did a cope where let's say I had like a ketone here. And afterwards, right, I would have something like this, not exactly that actually. I'd have something like this, where now the ketone is conjugated, right? So that ketone is now conjugated, lowers the energy of the system, increases its stability, pushes this incredibly to the right, okay? Cool, so think about, transformations that are possible that can increase stability. Those are the copes that are gonna go the best, okay? Now, I can't remember if I talked about this in the last one, so we'll talk about it now, unless there is an example here. I don't think there is, so we'll talk about it again. I think I might have talked about it in the last one. But when it comes to Claisens have kind of the same idea, right? So clasins are allyl-vinyl ethers, right? And so I could have a bunch of crap on here. Doesn't really matter, right? In the grand scheme of things, I'll just end up with something, that works, right? So I could have an allyl-vinyl ether. Again, the way you recognize it is because it's allyl-vinyl. So a side where the pi bond attaches directly and one where it's one away. Okay. And so I can kind of draw this stencil over here where I have, this guy over here, this allyl-vinyl ether. And when I heat this, right, all I've got to do, right, is take what I draw my thing again. The vertical bond I send to the back, so I send it to the far right here. And then these two push forward or push to the left, right? They kind of move up. Okay. And so that is my my clasin, and how you can quickly draw it. That's what happened there. So let's go do some numbering, right? Let's say I start from the allyl side, 1, 2, 3, 4, 5, and 6. Oxygen is 4, so this will be 4 here. And then the allyl side is the 1, 2, so that'd be 1, 2, 3, like that. So 4, 5, and then 6. So that would mean that 6 would be here, 5, 4, 3, 2, and 1. I can get rid of this now because I don't need it. And now I can just report groups onto my new clasin product. So looks like 5 has a methyl, 6 has an ethyl, 1 has a dimethyl, right? 2 has a propyl, and then 3 has a carbonyl, which will drive the reaction a bit more to the right because we're going from 1 carbonyl to 2 carbonyls, and we have conjugation now. Yeah, cool. All right, so that's the cope. I know I went over the phenol clasin trick, which was just that if we have this here, right? Essentially, if we have this here where this is 1, 2, and 3, right? The clasin rearrangement on a phenol puts it down here as 3, 2, and 1. So again, very quickly that trick there. Cool. All right, moving on. This one might be better looked at first when we think about, again, HBr just on its own. So HBr adds, the proton adds to the alkene, forms a pi bond. Sorry, forms a cation, not a pi bond. Forms a cation, and we got to form this one here or this one here. Both are secondary, but again, think about concepts, right? Not only do we want a secondary cation, but we want a stable one, and the position here that's stable is going to be the benzyl. So we form the benzyl cation to which Br minus adds in. And so what we end up getting out of this is the benzyl bromide. Okay. This is the same thing as if I used NBS, right? NBS would do the same thing, right? We would form the benzyl cation, or say the benzyl radical, which the bromine radical will react with, right? Cool. Where HBr gets a little different is that instead of, forming the initial radical via abstraction with a hydrogen or whatnot, what you actually do is you form the initial radical with bromine. So this, when we initially react, right, will form this here, right? So the benzyl radical does form, but the bromine is the electrophile, quote unquote. It's the first thing that adds. So when we add an H in the next step, right, it gives us what we would not expect. So HBr-ROR is sort of like an anti benzylic position promoter, right? So we do get the bromine here, but it follows the chemistry that we know, right? It follows the fact that it should have, the first radical is formed here, but we just chose to add bromine first, right? With that ROR. Cool. All right, moving on. N-butyle, again, we have a benzene with a benzylic position. N-butyle is a strong base, can also look like this. And strong bases like protons that are acidic, and at least N-butyle is the strongest base in the world, so it can, not the strongest, but it's up there. But that can deprotonate a benzylic position to form an organometallic or organolithium here, right? So an anion. And remember, organometallics, they add twice to carbonyls like esters and acyl halides and hydrides. So the point here was just to remind you guys of that chemistry, right? We'll form a tertiary symmetric alcohol. Right, and so a lot of you probably saw this on the key and thought, oh my God, right? What is this like weird monster that was born? That was just a result of organometallics on an ester. So remember the R group, right? We kind of just put down the middle, but we add two symmetric groups just like that. Okay, you could have drawn this in many ways. I just drew it the way that I thought was the easiest. So cool. All right. Next one, I mean, NaNO2 is also kind of a buzzword kind of thing. You see NH2, NaNO2, this forms the N2 cation, right? And then usually the copper salt is what replaces it in the next step. Whatever the nucleophile is the next step usually replaces it. Sorry, this will be a CN. And then again, going back to midterm 1 material, hydrolysis of a nitrile just gives you an acid. Okay, so kind of combining all concepts here, right, from all chapters. Cool. Anything could have been second step, right? Just depends on what you wanted. Cool. KMNO4, benzylic oxidation. If I treat this as my main benzene, then these are my benzylic positions, and I have H's there. So I get my naphthyl diacid. Second step is a heat step, so we get a closing, and the nitrogen is the nucleophile here, or at least it's going to be what ends up in the middle there. So we end up with a phthalimide, which again is the Gabor reagent. So the point of this question was to show you that you can build the phthalimide, the Gabor reagent, from scratch. You can make it from naphthalene. So don't be surprised if you're expected to do something like this, to do a synthesis forward on, right? You can now do your primary amine syntheses depending on whatever R group you add onto this. Okay, cool. This here, again, another buzzword reaction. You see NaOH, you see CO2. That is a Kolbe reaction. That's just going to do ortho acid formation. And so a lot of people, when they saw this, thought, why is it that it forms this and not the para product? And that is because the Kolbe reaction relies on a kinetic effect known as orthometallation. So, oops, sorry, not that. This here. So why is it that we don't get this? Because it relies on a kinetic effect, which is orthometallation. That's just a fancy way of saying that the Na metal kind of holds the CO2 and the oxygen here, and so that such that we get a first attack on the ortho position. So interestingly enough, right, ortho is the first position to be attacked, and it's just, it's a kinetic effect, right? That's why it's happening. Now, is that saying that para is impossible? No, it's not. All it's saying that if you control the equivalency and you control the time and the rate, or you control the time of the reaction, keep within the kinetic window, you can get majority of the ortho product before it starts adding para. It is totally possible to add para, but the first addition will always be ortho. So there was also another question that came out of this as to why is it that then the phenolic ester, or sorry, the phenolic resin adds both ortho and para. It's because we heat this up, we let this run for hours, right? This is a thermodynamic condition. Or I guess rather than saying thermodynamic, it's just the point is that we've gone past the kinetic time window. So it is totally possible and very much likely the case that the first couple of additions are the ortho, but you let this run long enough, right? And several of these will start to switch over to the para, right? Totally possible that can happen. Okay. Remember, thermodynamics, you promote reversibility. So a couple of these will probably reverse, and then you start getting the para attack, which technically should be more stable, right? Because it is opposite, it is far away from that carbonyl. Okay, cool. All right. Look at the last one. We just have H2PD, so benzylic hydrogenation. So this guy's going to get cut, or sorry, from here it's going to get cut. We get a toluene, and we get an acid. Remember that triple bonds and double bonds are not safe from this reaction, so this is also going to reduce down as well, right? If there were like an alkyne that would also have died in this, there was like a alkene, even actually here, right? An alkene would have died to this, right? Benzene does survive though, because its stability allows it to get away from easy hydrogenation. Cool. With that, that's the predicted products. Hopefully not too bad. Pretty straightforward. I expect this to be around the level that you would expect. So yeah, cool. This mechanism, again, we have 3 components. We have an amine, 2 carbonyls. It's essentially just a manic. Just be very careful. A lot of you probably did this instantly to get that cyclization. And while that is totally possible, if we look at the product, it's not really going to work out. Because you can see here, the ketone is on the outside. So point of this was to kind of relay to you guys, oh, look, this is actually going to attack the aldehyde first. So to kind of get really just very, very rudimentary, easy way of doing this, right? You'll form this aminium here, and then, right, 1, 2, 3, 4, 5, 6, right? This is what's going to go ahead and attack, right, when it analyzes. So just kind of doing a lot of things very quickly. That's the analyzation. So what you end up getting out of this, right, in this 6-membered ring is going to be this here, where we have the ketone kind of flying off here. Okay. Now, one way that we could have sort of predicted that this was the outcome of events rather than cyclizing, is we can actually take the manic product and decompose it, right, or deconstruct it. Remember, alpha, beta, we can cut across those bonds where the alpha position stays exactly the same. We do nothing there. And then the beta position, sorry, wrong color. Again, wrong color, right? The beta position, we just cut again, right? So we keep alpha the same, and then beta we cut again. And what we get out are our three components, right? We get out that we have NH2 and this ketone, which we already knew were there. But we can see that the aldehyde is what condenses first. So not only can manic elucidate to us, the three components of a reaction, it can also tell us which three, how the things add together. Right? Clearly, the aldehyde added to the amine, and then the ketone analyzes and then attacks in. Because I know I'm going to get this question a lot, just because this is how it is. It's okay. These are good questions, by the way. Why isn't it that we get the intermolecular attack? Why isn't it that we can't just do this? And the answer is pretty simple. In mild acid, it is still possible to get the protonation on the amine, and the amine can serve as a proton source. So when we're thinking of aldehydes and ketones in solution, it is possible that this guy could reach out and grab this, but not very likely. But this guy is floating around, could attack that, right? I guess both of these, it's fair, right? That both one of these two could take that proton. We're just kind of hoping that the aldehyde does it because it's more electrophilic for the amine to attack. And actually, really, the biggest point here is that, remember, acid is just a catalysis. It's just catalysis, right? It just makes reactions faster. Aldehydes are very electrophilic, so it's really reasonable that this guy would go ahead and attack here anyways. Okay? But I could totally see people thinking that this could attack here. Very viable, possible reaction. Just keep in mind that this is also a mechanism, so you don't have to prove anything other than how do I get from left to right. So don't overthink this one. Cool. All right. Second one, this is just phenolic resin. Main points here, right? You just kind of attack. You get the formaldehyde added on, right? We get this precursor to the quinimomethide, and then, right, you can just eliminate that off. Right, and then, I'm doing it all in one. It would be more of an E1CB where you first form the anion, and then kick it off. But you guys get the point. It's all this is all in your notes, so you really just go with your notes, right? And then, right, the phenol, another one of these phenol anions, and just attack him. Okay, cool. All right, mechanisms have never really been too bad. They've been pretty straightforward, so I'm not too worried about that. Cool. Now imagine everyone's important. Most interesting part in the part of this is the syntheses because they look so crazy. In fact, actually, I've been accused of missing a step on the first one that I wrote the key wrong on it, which I can understand why, but definitely the key is right. This first one is a bit of a doozy. You're going from this open chain nitrotoluene to this closed N-nitrosamine. For reactions like this, this was mainly just meant to be, just 21 type reactions. You can see down here, this is definitely like a 22 level, like a chapter 22 level synthesis. But if we just kind of think about transformations we know to simplify this, I know that N-nitrosamines are made by NaNO2, right? So at the very least, I think that I can simplify this down to here, right? To the indane. This is known as an indane. Okay. And I think to myself, okay, because that's, that makes sense. Secondary amine with the NO2, that's where that's coming from. So how in the world do we go from this NO2 all the way over to here? Well, one thing you might notice is that if we look at what's being added, right, in the transformation, we're sort of adding in at least this carbon here, right? And we have sort of this nitrogen also that's kind of hanging out. So we've kind of added in a carbon and a nitrogen, and we can see that's being added in here. Not only that, but we also notice that, hey, look at that. We are, it should be carbon, writing a carbon, then a nitrogen. Yeah. Not only that, but we can also kind of notice here that this nitrogen or whatever is sort of adding to where the NO2 is or used to be. And so if we think about intermediates for that, right, that must mean that this NO2 could be from a diazonium, right? Because we know NO2 we can turn to NH2, and then NH2 we can turn into N2 plus, right? So it makes sense that if we're using a nitrogen nucleophile, that possibly there was an N2 plus there that's causing the cyclization. So I'm going to go ahead, right, using my knowledge of how I can do a substitution on that NO2 position and say, I think maybe there was an N2 plus here, and then there was this sort of nitrogen chain that kind of closed on. Okay, and so I mean, from this, the N2 could have been right an NH2, right, and then the NH2 could have been an NO2. Okay, so that's how I simplify this problem to start make a little more sense as to where did things come from, right? Because again, I notice that an N is substituting the NO2. What's the only way that can happen? It's got to be that it's from a diazonium. Okay, so that's what I'm noticing. When I get to here, though, again, all that's now changing is how in the world am I adding this CH2 NH2 onto the carbon there, and CH2 NH2, that should be a very, very, suspicious fragment, or a very, very interesting fragment, right? What can we think of that can add to a benzylic position that might have CH2 NH2? I can only think of a couple things, and I'll let you guys pause and think about it if you want to, but CH2 NH2, that's almost laughing in your face that it's a nitrile. So I think that the CH2 NH2 is from a nitrile that we reduced into a CH2N2. So I think that this here was CN, and then when we did the H2PD step here, or whatever you want to do to reduce it should be H2PD because you want to reduce this and you want to reduce this. That's how you get to here. So for those of you that were confused, how in the world did I manage to reduce this down? It's H2PD, right? It's a triple bond, so H2PD will reduce it down, right? I'm pretty sure that's in your notes too. And then from here, this is just NaNO2, HCl. Right. But from here, right, CN minus is just a nucleophile, and especially at that benzylic position, which we can activate with a bromide, I have absolutely no qualms on that happening. You can do this activation here with NBS, BR2 if you want to, it doesn't matter. Right, any reasonable radical brominating agent will have worked here. NBS is just much more practical, much more real life based. But that's how we crack this synthesis apart. Okay, at the very least, we can write something respectable onto our page, right? Something that will work. And then we can go back and see if any step doesn't really make sense. So, I look at the first step, I can get the bromination, that should work pretty fine. CN will work very well on the SN2. H2PD will reduce down both of my amines. Where this gets a little tricky is the NaNO2 step, because, well, wait a minute. This is a primary amine that's not conjugated. This is an amine that is conjugated. If I think about which lone pair attacks NO cation first, it's probably this guy here, actually. This guy here probably attacks the NO cation first, which that means that actually our primary amine is what's turning into the N2 plus, which that's okay because aniline is still a respectable nucleophile. It'll still go ahead and do the attack there. So what we predicted to be the N2 intermediate isn't actually the N2 intermediate, but that's okay because we're going back. Nothing really changes. So indeed, actually, the nitrogen is totally retained throughout the reaction, right? This nitrogen is the same one. And then in that same step, right, there's still NO2 floating around in solution, right? This will just go to here, right? This is just an intermediate. This is not actually isoluble, this indane. It will just instantly nitrate. Okay, cool. So when we're thinking about these reactions, right, especially with substitutions, always consider what substitutions are possible with what you have, right? I gave you the NO2. That should have at least rang some bells, and I think I need to make an N2 plus. Okay, usually what you got to do there. Okay, this is a tricky one. So if any of you guys got it, that's great. That's great. You have the eye, right? You have the eye to see things. Cool. All right. You can imagine there's a lot of things we could have used here too, right? We could have. There's so many things we could have added to this position. It's a benzylic position, so maybe we could have done some anion type stuff, something cool there. Like for example, maybe we could have, will this work actually? Let's say we added a carbonyl. Let's say let's say we did like an N minus here, and we add a carbonyl, for example. Actually, someone did this. They decided, this indane is the result of an amide coupling. That could work too. This is just a lot longer, and again, if you kind of retro here, I don't know. I guess I don't really see how this comes up. I think if anything, if I retroed here, I wouldn't think that this is an amide. I would think that this is a NH2 coupling with some carbonyl like this, and then try to figure out how in the world I can make this happen, like this addition here, which that could maybe work. Like maybe you could do, oh, maybe something I'll accept is you could say you form this bond via the alpha alkylation of an aldehyde. I could totally see that. I mean, just think about like if I had to write something down, I could see that happening, and then kind of coupling those together and doing a nitrosyl cation there. Okay, I can accept that. I'm not too confident that this is the best version of this, but it works on paper, right? Totally works on paper, so I'm willing to believe that that could possibly happen. But yeah, let's actually let's see here. If I add in the aldehyde and I do this here, could I get a 1, 2, 3, 4? No, I wouldn't get a good ring. They'll give me a 4-member ring if I did some kind of like diazo stuff here. Oh well, cool. I mean, again, the point of this is just to think different things that can happen, different things that we could do here. I like this one though, so I'll if you're watching this could have totally worked too. Cool. All right, so that's the first one. Hopefully that makes a little more sense. I think the first one was a bit harder than the second one because the first one is really kind of hard to see. I think the substitution there. But this, I mean, it looks difficult, but it's just a slurry of reactions. Okay, so whenever you get a synthetic target that's really huge and really scary, always try to simplify it. Just think of things that you can get rid of, so that you can start to think about what are possibilities, what are some reactions you can do. For example, I'm looking at this overwhelmed, but I do notice I have a phenol with an alkyl chain next to it, and in particular, I notice that this alkyl chain is allyl, right? Allyl alkyl chain, that's screaming Claisen. So at the very least, I can start to simplify and say, okay, retrosynthetically, this is just a Claisen, so that comes from the phenol, right? Claisen is just you add a carbon chain to the alcohol, heat it up, and it Claisens, right? When I look at this amine chain here, I might feel overwhelmed, but I notice that this amine has 5 carbons in an amine. This also is 5 carbons in an amine, right? So I'm thinking possibly, I mean, if I'm forming an alkene from amine and we have a ring opening, it's only really one reaction here, right? It's a Hoffman. So possibly I have, right? Oh, sorry, not morpholin, just piperidine. I might have had something like this where I did a Hoffman elimination. So I'll start writing these down. So Claisen rearrangement, Hoffman elimination. So here's where, you might get a little stuck and you might think, okay, how in the world do I get 2 nucleophiles on that are paired to each other? Well, let's consider how nucleophiles can add to rings. There's really 3 ways we can do this, right? We can do SNAR, we can do diazonium, we can do PD, and then we can do benzyne. Now, I'm going to start off with this, and this is always the case. Try to never do benzyne. Benzyne, if you didn't already kind of catch the memo, it's the worst possible reaction. Actually, I have to correct this. So on the other midterm, I talked about how if you had a chlorine here and H here, right? Steric effects would dictate that this guy is taken. You guys never talked about steric effects. So actually, in fact, it wouldn't matter which one was taken. You could form either alkyne here. So you'd form this one and this one. So all 3 positions are actually open for attack. The other thing I did notice was that these 2 are actually the same. I wasn't concerned about that in terms of concept. I was just concerned with, if you have an alkyl chain, either side could add. So I apologize for having not seen. It's a trivial thing, but essentially, right, the chlorine could be here or it could be here, right? Again, remember that notation where if I just put a dash through the middle, it could be on either of those carbons. So there's technically 2 products, right? One where the chlorine is on one of these carbons, and then one where it's on the right side here. I guess, well, really it's, I'll just draw it, whatever. Right, because they're technically just the same, right? So there would be one here and there'd be one here. Okay. And if you wanted to, I mean, if you ended up drawing this one too, like it doesn't matter. They can't dock you for drawing the same answer twice. That'll be weird. But yeah, cool. But anyways, benzyne, as you can probably tell from all the reactions and all the intermediates and all the products, worst one to do in synthesis. So try to avoid doing it. Okay. That leaves you with PD, N2, and SNAR. Okay. Now, what are some tells or some things to look for? Well, we just saw for diazonium. One of the best ways to know to do a diazonium is if you're just given an NO2. NO2 is, I mean, that's what you need, right, to do a diazonium, because that gives you the NH2 that go to N2. So if you ever just see just like kind of on the spot, I mean, if there's an NO2, it kind of keys you in that you have to, they want you to do a diazonium type reaction. It could also be if, like, for example, let's say that you notice that at the end product, you have like two things meta to each other, right? So for example, let's say I have an NO2 and then let's say I have some nucleophile that's meta and then another nucleophile that's meta, right? There's absolutely no way to do this on your own other than using NO2, because NO2 you could add in a bromine or something, right? Kind of as a placeholder for now. Do your diazonium on the NO2 to get out the N2 and then a nucleophile. And then the bromine, right? I mean, obviously the bromine and this guy here are meta to each other. So SNOR is off the table. Again, benzyl would be off the table. N2 would be off the table too, right? But the one thing not off the table is PD, the cheat code reaction, right? PD kind of doesn't really have any rules other than you can just use it, right? As long as you have a bromide. So you could use a PD coupling and get a nice meta substitution, okay? So things to think about, right? The fact that we can have this meta substituted thing here with the nucleophiles. We don't really see that here. So I know that we're not going to the NO2 because those guys are para. So that leaves us with only SNAR. And so what can SNAR offer us that might give us something meta? Well, if I think about the SNAR sequence, you can start from a benzene, you can chlorinate. So kind of doing the opposite that we did with the diazonium, right? Instead of nitrating and then brominating, we chlorinate, and then we nitrate. Notice how the one addition para of the NO2 kind of activates it towards SNAR. So you can go ahead and SNAR, get your nucleophile on, right? And then afterwards, you can NO2, right? You can use NO2, and you can get NO2 groups on using the N2. So you can get another nucleophile here. So one way to kind of tell the difference between a diazonium, like they're forcing you to do a diazonium or they're forced to do SNAR, is to think about where the nucleophiles end up against each other, right? If they're meta, probably the best route is to do diazonium into bromination and then do a PD reaction, right? That's how you get that meta substitution. On the other hand, right, if I want to get a paratype paratype relationship, I'm looking at possibly doing a SNAR, okay? As we can see in this, I mean, they're para to each other, so I'm probably doing a SNAR here. So if I kind of just get rid of this stuff here, right, I can consider that maybe I'm doing some type of SNAR where if I think about this NO2 and Cl, right, actually, let me write it kind of here, right? The phenol we could just get from NO2, right? This is the diazonium hydrolysis. And then I could have just added in the piperidine via SNAR on the chlorine side. Okay, that's totally possible. So again, these are just some key traits to look for to kind of help you out. With PD, again, that's kind of a cheat code. So if you're absolutely lost, actually what you could have done is you could have just thought, okay, well, I have absolutely no idea what to do here, right? I have an OH and I have it looks like my piperidine adding into the ring here. If I had to absolutely think of a cheat code reaction I could do here, I could just pretend, or not pretend, but I could just say that the bromine used to be here and I did a PD catalysis. So I didn't put this in my key because I didn't, this is, again, it's a cheat code and cheating is not fun, right? But the point is still there, right? If you're completely lost, you can really make any, I mean, we didn't start from a benzene, so we could really make any benzene we wanted to, and then just go ahead and PD it and get that group on. Okay, cool. So that's my little blurb about SNAR and N2 and PD and what to think about and how to know when to use it. Those are really the most important things to get out of this. Okay, but with that said, right? I mean, we can even go from here, right? I mean, this is a starting material, so this is basically the end of the synthesis. Okay, cool. So if I were to write a synthesis for this class or think of the hardest ones, I think these two are the hardest possible ones because they kind of incorporate all the concepts you need to understand how to do things. They also kind of elucidate to you the complexity at which you can make these things. I mean, if any of you have looked at it, I don't know if you have, but you could, I mean, these chapter 22 reactions, I mean, ask anyone, ask your TAs, ask Helix, ask your parents, ask your friends. These are the reactions used every single day in industry, used by pharma companies. This is medchem. This is basically medchem. So, oh, hold up, sorry, I pulled up the wrong page. Oh, cool. Open. Cool. Hope you guys can see this now. But if we look at the synthesis problems for this mechanism, for this midterm, right? I mean, this is literally a drug target. This is SR 17018. You can look up the synthesis for it. Biologists figured out in 4 steps. You guys can too. Okay. Very, very complicated target, but it requires very simple reactions that you guys already know. In fact, I'm willing to go through this with you guys because it's a favorite of mine because of how simple this is. So probably the simplest bond to figure out here, or I mean, if you just think about bonds you could make, if we kind of look for the core, right? The core is right here. So we can kind of see things that are going on, right? For example, we see that this NH2 is making a bond with this benzene here, and we have these chlorines on, and then we have this nitrogen over here. Really, the key thing is that we have a nitrogen over here because this nitrogen could have been an NO2. So I'm thinking that we're doing some kind of SNAR to get on this nitrogen onto that ring. So I'm thinking this is going to do a SNAR. Okay. On the other hand, right, I've got this nitrogen here, right, this guy over here, and it's making an NC bond, right? Again, NC bonds, really only one consistent way to make it, reductive amination. So I'm considering that we're doing a reductive amination, possibly with this aldehyde, right? And then the amine there. So with just that, I've already simplified up to the point of what my main two reactions are, right? I'm doing a reductive amination on the secondary end, and I'm doing a SNAR on the primary end. Now, a lot of you guys were wondering, how do I know which one goes first? Remember that secondary amines, both in gas phase and in liquid phase, which the phase that matters, secondary amines in the liquid phase are the most basic, so they're the most nucleophilic. So you could get away with one equivalent doing the reductive amination first. So we could do the red am, right, to get on this part here, right? Again, doesn't really matter because we're just doing reductive amination. But now we can go ahead and do our SNAR. And again, when I think about my SNAR component, I know for a fact, again, we can put like a Cl here, we can put a Cl here, and then we'll have, again, the N, and then we want our N to attach here. I could put a Cl here. I would put an F just to promote the fluorine. Remember, the order of SNAR reactivity for leaving groups is F, Cl, Br, and I. So it's electronegativity now that matters, not size. But I could do that to promote it. I mean, this is also going to be ortho to the NO2 group that I think is this N here. Anyways, so it's totally fine what you do here. But anyways, we can go ahead and SNAR that on. The very least, you guys can get to this point here without having to start pull out the big brain straps, right? To actually have to think about how in the world you guys are getting on, right? How in the world are you guys getting on the that weird little diamide thing? This is actually super simple if you think about it. I mean, if we kind of break this bond here, like let's say that, you know, or we can even do this here. We can break this bond, right? When I think about forming, when I think about forming amides, I mean, every derivative can do it. Probably the easiest derivative that can do it is an acyl chloride. So when I reduce this NH2 to NH2, right? Again, I'm thinking, okay, if I break this bond, this is just an acyl chloride, so I have an acyl chloride here. If I break this bond again, right, I'll just have another acyl chloride. So this here is called phosgene, very reactive intermediate, incredibly reactive actually. It was used in the formation of mustard gas, I believe. But a safer variant of this is if you just use the diester, the carbonate, which hopefully for those of you that took that exam got the points back for that. It's actually not the case that this is less reactive. It's actually way more reactive than an ester. In fact, that's why it's used in industry. The safer version of phosgene, right? If this were less reactive than an ester, we would never even use it. But it's an incredibly important reagent. Okay, but that's actually all that is. So it looked terrible, but it actually wasn't. But at the very least, you can get to this point here, and then you can kind of scroll your brain to figure out how in the world do I make two amides there. Very simple, right? You just kind of phosgene it, or you use the carbonate, and then you carbonate it again, right? Or you kind of just let it cyclize. Okay, so cool. I mean, you guys now as pre-meds made a actual real drug target. Okay, SR17018. Okay, it's pretty cool. I think it's pretty cool. Got it down to 4 steps, right? Which is not too bad at all. Cool. Now, when we look at this one down here, right? This one is a derivative of a drug. There was another drug. I mean, it looked kind of like this, but there was a lot more complexity on the nitrogen end, and I didn't want this to be too long. So I kind of cut it down to the intermediate towards a drug. I forgot the name of it. I can actually just look real quick. I got this on Drug Hunter. Drug Hunter does molecules of the month, which to kind of go over small molecules that are killing it in the pharma industry right now. this here, what I have drawn is a derivative, or it's a type of DKY 709, I believe. I think that's, I mean, it looks kind of similar to what I have on the screen here. So, you know, that's where I got that from. Okay. But anyways, when I look at this, right, again, I'm looking for bonds that are easy to deconstruct, at least easy for me to understand. And really what it should have been the first thing that kind of caught your guys' eye is this over here. This over here is this amino ketone. There's actually, I forgot the common name for this. I think ketopipridine. But anyways, if you look at the ketone and you look at the amine, maybe now you guys will be able to see what the relationship is. These are, oh, sorry. These are manic. This is a manic cycle because we have a beta amino ketone. And if we think about in manic, what we have to do, we cut, right, the alpha from the beta. Right, so we cut the alpha from the beta, and then we say, okay, we have these beta carbons here, right? And then the alphas, they just stay the same. So we use acetone in this, right? The betas, we just cut again, we cut it off the N. And what we get in this case is NH2 and formaldehyde. So my 3-component reaction here is probably the simplest thing ever. It's an amine, formaldehyde, and acetone. This is my manic. So I know now that I just did a manic to get to this ketopipridine, which is pretty cool, right? And now I can start to think about, again, what are simpler ways that I can have this, what are very simple ways of forming this amide ring over here? How could I do it? What could I do? Again, amides, you can consider cutting that bond there like we talked about. And this could be like a chloride. This could be whatever you want. The whole point is that it is an acid derivative. And I kind of look at, if I look at that position, right? If I look at that position where that acid is forming, or that acid chloride is forming, it's also the benzylic position. So look at that. I can actually say that this was an OH, right? Because that could have been a benzylic. And then I can say that, okay, that just means that that's just that methyl, right? That's just that methyl from before. So now all I need to figure out now is where in the world did these two CH2, NH2 fragments come from? And hopefully our discussion earlier kind of narrows it down. CH2, NH2, that's just nitriles. So I have ortho-para-nitriles to this toluene. Oops, I kind of gave it away. But if I think about how did I get these nucleophiles ortho and para to this guy here, again, this is not an EWG, so SNAR is kind of off the table, right? I can't really, get those there with SNAR. But I can add in NO2s on this, I could make these NO2s that I, reduce down to NH2 and then N2 and then, dicyanide and then reduce from there. So that's how we get back to here. So look at that. Very complicated drug targets, but they're, littered with common reactions. That's the whole point of chapter 22. My biggest advice for people that are taking Chem 131, this is the main bulk of it. This is the most important thing. If any of you that's interested in organic chemistry and med chem, or like doing this stuff in real life, I mean, this is all that it is. It's all chapter 22, 21, 22. Okay, because that's what medicinal targets are. They're amines, they're heterocycles. Heterocycle chapters are going to be super important actually when we get there. It's my favorite chapter. It's what I'm going to grad school for. Is learning how to build those guys and make medicines. So for any of you that are interested, always welcome to hit me up for advice. But I'll tell you what, my number one advice is your job is to do very well on 21, 22, and chapter 25. Okay, cool. All right, so I'm going to call it there just to keep this video pretty short. I think I probably hit an hour, which is good for a key. The rest of this stuff, I'll just kind of give hints. This is a tandem reaction. This is a tandem reaction. Tandem, this is it's a SNAR, you can tell hopefully. Tandem. This relies on basicity, which amine is more basic. This is very related to this question here, which I gave a very big hint to earlier in the video. So if you can solve this, or if you can solve this, then you know how to answer this question. Tandem, kind of tandem, and then tandem. Well, no, not really tandem. This is just one reaction. I hope you can see. I mean, it's a ketone, ketone, amine, and ketone, aldehyde, and amine. We can actually draw this one very quickly. That will just go there. So 1, 2, 3, 4, 5, 6. 6-membered ring. right? And then, I mean, kind of really made it really suggestive, right? It just goes there. So 1, 2, 3, 4, 5, 6. Oh, wait, what? Did I mess this up? Oh, sorry, haha. I did mess this up. So this should have been there we go. Now this will make more sense, right? Attack there. 1, 2, 3, 4, 5. Wait, what? What am I messing up? I'm doing something wrong here. Anyways, or either I mess this question up or I probably messed it up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. No, what am I messing up? Oh, I see what I'm messing up. This here will bond to this here. There we go. See, don't do things in your head, guys. I can't even figure it out. Okay. And then this claps down there, which makes a very honeycomb looking, looks kind of like a honeycomb, which you guys can imagine why I might have chose a honeycomb looking manic, right? Okay, cool. That's a really ugly bee. Let's draw a better one. Yeah, cool. All right, well, I'm going to call it there. If there's any questions on 3A, please let me know. I'm not planning on making a video. It's just not enough time. And a lot of these were egos, to be honest. I really like writing these kind of questions. But yeah, any questions, just let me know. You guys have a good night.